Hey, okay, so I'm gonna do classwork problems number 2 and number 8 on the enthalpy classwork. I have number 2 written already, so it'll kind of speed up the time, hopefully. And then we'll do number 8. Also, if you have any questions, you can email me. But I think that this is pretty simple for most of you. I'll also do a couple more at some point also. All right, so let's see. This is number 2, by the way. So let's start. We're going to do 2, and then we'll do 8 after this. All right, so this is a kind of a combustion reaction, except for we're not combusting a hydrocarbon. We're going to, so boron, element number 5 on the periodic table, is being burned in a combustion reaction with O2 to produce B2O3. S and G, of course, are just the solid and gas, the forms. All right, the equation, when balanced, will have an enthalpy value of 2,543.8 kilojoules being released from the system to the surroundings. And I know that because of the negative sign, right? Negative enthalpy means the energy is being released. Okay, so the first thing we need to do is we need to balance this. Well, let's see. We have B2. We could go 2B here. All right, and that would balance it out, and then you'd find out your O's are off, and you'd have to do a 1.5. So why don't we go 4, 3, 2. All right, so now the equation as written is 4 moles of boron combined with 3 moles of oxygen gas, diatomic, will produce 2 moles of B2O3, and when that happens, the enthalpy value is negative 2,543.8 kilojoules. All right, well, this really isn't that bad. All right, so this is the amount of heat energy when you combust 4 moles of boron. So let's figure out what we have here and get that into moles. Well, 2.75 kilograms of boron. If you have your metric sheet, you just move the decimal point 3 spaces to the right. It's going to end up being 2,750 grams of boron, right? Down you move right, so you go 1, 2, 3 spaces, be 2,750 grams of boron. Okay, boron on the periodic table. Now, I don't have my periodic table in front of me, but I'm pretty sure that 1 mole of boron is 10.81 grams of boron according to our periodic table. All right, so we're going to have somewhere in the neighborhood of 250 moles of boron here, 3 sig figs. So you know what? I don't care about sig figs. When I did the calculation earlier, I came up with 254.4 moles of boron. And you might be like, Staraj, that's an awful lot of moles. Well, yeah, it's an awful lot of moles because it's an awful lot of grams. It wasn't 2.75 grams, it's 2.75 kilograms. Yeah, that's going to end up being a lot of moles of boron. All right, now, let's figure out what we can do. We can say that it's this heat value for 4 moles, or you could divide that by 4 and multiply it by, by how many moles you have. I'm just going to do it this way because I already have it set up this way and it's going to be simple. So we got 254.4 moles of boron, right? I'll put that over 1, kind of like this, all right? Now we need to figure out the kilojoules. Well, this is the heat value for 4 moles. Okay, well, if I want to just figure out what the heat value is for the number of moles I have, I'm going to put the kilojoules of the reaction, negative 2543.8 kilojoules per every 4 moles of boron, like this. All right, now where am I getting those numbers from? Here. All right, here's my 4, right? That's why I have 4 moles. Moles of B and moles of B will cancel out. That's the enthalpy value per 4 moles, or you could say it's going to be, well, 6 times 4 is 24. It's going to be probably 600 and something kilojoules per every 1 mole, but why add the extra step? All right, so our answer is going to be 254.4 times negative 2543.8, and then divide it by 4, and I get this as a numeric answer somewhere in the neighborhood of negative 161,786 kilojoules, which I rounded to negative 162,000 kilojoules would be the enthalpy value for 2.75 kilograms of boron. Okay? So, that's it. Yeah, it's really not that hard. It's really not that hard. Okay. So let me take a look at number 8 on the classwork, but number 1 in your hearts, I'm sure. All right, number 8 says, I'm going to erase this. I'm going to try to multitask here. All right, so we got, 2.75 grams of KClO3. I would have showed you a really, really, really cool reaction had we been in school where I would heat up some potassium chlorate and I would heat it to the point where it becomes molten. And it's a salt, which means it becomes molten at a very high temperature. All right, but anyway, I would put that in a test tube and then drop a gummy bear in, and you get a really, really, really cool exothermic reaction. All right, so what I said, we got 2.75 grams of KClO3. So let me write down my pertinent information. Okay, and we're dissolving that in 65 grams of water. 65.0 grams of water in a coffee cup calorimeter. Again, it's not a perfect calorimeter. It's not completely adiabatic, but coffee cups are pretty good, right? Coffee cups, like a styrofoam cup, keeps the heat of your coffee or your tea or your hot chocolate in better than, say, a mug would, because when you feel the side, you don't feel the heat coming out as much as if you have it in a mug and you feel the side, it's losing heat to the surroundings. All right, so when we do that, the temperature changes from 24 degrees Celsius to 20.7 degrees Celsius. All right, so this is a temperature drop, right? We're starting at 24.0, me and my sig figs. There's our T1, and the T2 is dropping to 20.7 degrees Celsius. All right, well, we need to figure out what is the enthalpy of this process in the kilojoules per mole. All right, well, we have two things. The water temperature was not going to change, relatively speaking, until we drop the potassium chloride and dissolve it all up, right? All right, so the whole thing then is there's a Q value for the KClO3, and there's a Q value of the total solution, and it's going to add up to 0. So what made the water temperature drop is the stirring in of the 2.75 grams of KClO3. All right? So we need to figure out the enthalpy of this. This is making the water temperature go down. So the solution's temperature's Q value is dropping. So it's got to be negative, which means this has got to be positive, and they're the same number, right? Like -8 and +8 are going to equal 0. Okay, well, the Q of the solution is going to be the thermodynamic equation of Q is equal to M times delta T times CP. Okay, now hopefully I have instilled enough knowledge into you almost people that you know, without looking it up, without putting your hand up in class, Mr. Drachy, what's the CP? Water, right? You should know that the CP is 4.184 joules per gram degree Celsius, or 4.184 joules per gram Kelvin if I was using Kelvin temp. Now, it is mostly water. That's why the CP is probably not exactly 4.184. It's probably a little bit different, right? But it's close enough. All right, so let's start plugging in what we know. The Q of the solution is going to be these two added together. It's not the Q of water, it's the Q of the solution. All right, so let's add up our numbers here, and we'll plug in our mass. So we got 60 grams, or 65 grams, I'm sorry, plus 2.75 grams is going to give us an M value of, what do we got? 68.75 grams, or Uncle Strach likes to call them little baby G's. All right, so there's our 68.75, or no, 67. Ugh. Get rid of that, sorry. 67.75 grams. That's better. All right. I'm no longer perfect. All right, well, what's our delta T? Delta T, of course, is T2 minus T1. So 20.7 minus 24.0 is going to be a negative change, right? We're going to get minus 3.3 degrees Celsius, okay? And then, of course, the CP is 4.184 joules per gram degrees Celsius. You probably hear my little man singing in the background over there. So, hey, we're all trying to deal with this the best we can. All right, so let's get rid of the baby G's and the degrees C's. Ha, there you go. I could be a rapper. All right, so that's going to make the Q of the solution then. I didn't round here. I just kind of kept it. So the Q of the solution, I can't write, kids. The Q of the solution is, what'd I say, negative 935.44, and I'm going to call that joules. And I'm calling it joules because that's the only unit left. All right, so this is the Q of the solution, which is negative, which is going to make the Q of the KClO3 the exact same number but positive, right? And since that heat was given off by the water, then what we have is a Q of KClO3 is going to be positive 935.44 joules. I'm going to stop here for 1 second, okay? That is the number of joules that was taken in by the loss of the water from the solution. So it's that many joules per 2.75 grams, right? That's the number of joules taken in by the 2.75 grams. I was saying before, this is kind of like the way cold packs work, although cold packs use ammonium nitrate, NH4NO3. But it's the same basic principle here. Okay, so it says, what is the enthalpy value in kilojoules per mole? So this is the unit I need. Well, joules to kilojoules is easy. So let's go, we got 1 kilojoule is 1,000 joules, and that will get rid of my J. Okay, so as of right now, I am in kilojoules per gram. So what you would do is you would go to the periodic table and you'd figure out what the mass of KClO3 is. So you got to do potassium, which is 39.1, plus chlorine, which is 35.45, plus oxygen, which is 16, and multiply it by 3, which is 48, and add them all together. So since I did that a little bit earlier, its molar mass is a buck 22.55 grams is 1 holy moly of KClO3, and we get this kind of a situation. I'm sorry, I'm at like the very, very bottom of the paper here, or the paper. What is this thing called again? A board. I've been locked up in my house so long, I think I'm going clinically insane. But you can't tell, can you? All right, so we got our kilojoules on top. Only thing left, we got our moles on the bottom. And when you multiply the top, so 935.44 times 122.5, and then divide by 2,750, which is 2.75 times 1,000, you end up with an endothermic number of positive 41.7 kilojoules per mole. And then I can't mic drop, so I'll marker drop. All right? Okay, kids, I hope that was beneficial for you. And we'll move forward from there, okay? Keep checking Google Classroom for more updates from Uncle Starach, all right? Take care, guys. See ya.